Good afternoon, everyone. My name is Minji Chen. I'm an assistant professor of electrical engineering and analytics center at Princeton University, and I work on power electronics. Today it's my pleasure to introduce Professor Seth Sanders from UC Berkeley to come to us and talk about flywheel energy storage. I've known Professor Seth Sanders since I started studying power electronics, and many of his papers has inspired me a lot. Professor Seth Sanders' research expertise covers the widest power range, all the way from nanowatts, milliwatts, integrated circuits, down up to megawatts grid-scale energy storage. And he has also contributed a lot to control and modeling of power electronics and the real practical implementation of power electronics. And the most important fact that I want to mention is that Seth is actually a Princeton resident. He grew up in Princeton, received his high school degree at Princeton before went to MIT for bachelor's and PhD, and then become professor in UC Berkeley. And this time is actually the first time we were able to get Seth back to Princeton officially as a speaker, and then talk about all the great work that he has done in power electronics. Okay, so let's welcome Professor Seth Sanders for his talk.
All right, thank you, Minji. It's indeed a pleasure to have the honor to be back in Princeton and to be a guest of Princeton University. Today was an amazingly full and interesting day, and I've been joking that, boy, I hope I got the job now. And thanks for being here to listen to this talk about energy storage and my favorite type of energy storage, the flywheel variety. So let me begin with an energy storage policy map, and what we're looking at is perhaps the beginning of an RPS type of map. So some of us are familiar with an RPS standard map for the US, where each state has a renewable portfolio standard, and it's a lot denser than what appears here. So I believe there's a lot more activity in the background, and many states are moving in. It's been a few months since I last tried to update this, but coming from California, I'm always excited to note that we were up front with our AB 2514, which mandated 1.3 gigawatts of flexible energy storage to be in place and functioning by 2024, and that was followed on by additional pieces. So New York and Massachusetts are following along, and Hawaii is one of the states that is quite aggressive with respect to its RPS standard and has a fairly complex set of rules for customers to implement energy storage. Yes, sir?
Are you alternating between gigawatt and gigawatt hours here?
Yeah, okay, that's a good point. I'm not purposely alternating between gigawatts and gigawatt hours, and it's sometimes a confusing point in talking about energy storage. So traditionally, capacity numbers for utility are in units of gigawatts, and units of energy storage ought to be in gigawatt hours, right? And nevertheless, there's some implication of relationship in terms of number of hours, and it's not always super well defined. And so people can make rules with respect to any unit they would like, actually. So that's a fair point, okay? Okay, so an important thing in having ambition to go after something is that it's big. And I think many of us would not argue that the opportunity in energy storage is large, and this is a picture of the global grid-connected storage that is projected and perhaps has already been implemented. And indeed, it's global, and perhaps largest pieces are in the Asia-Pacific region, inclusive of China. But each section of the world has its potential, and that's noted. So there are equivalent studies by the sort of parallel market studiers, and they all show very large numbers, and in many cases, the type of exponential curve that investors like to see, or maybe investors like to see, are often prominent. So this looks more like a linear growth curve, but nevertheless, definitely big numbers with many thousands of gigawatts, or sorry, tens of gigawatts. Okay, so why energy storage? So zooming down into a little bit finer scale, one of the favorite topics that comes up in California is the thing called the duck curve. And the duck curve basically is an indication that many of the potential applications for energy storage will see opportunities for multiple cycles of charge and discharge per day. And so the pattern that's illustrated here shows that going forward, the prominence of a 2-cycle-a-day opportunity becomes more prominent. And so what the duck curve portrays is the onset of more solar coming into the energy mix as the years go by, and the net generation supplanting load, and thus the net load curve being suppressed in the middle of the day. So that's the belly of the duck. And this type of pattern is actually replicated in a number of other markets around the world. So in some earlier visits to Hawaii, what people at Hawaiian Electric related was that we're way past that. We're the Loch Ness Monster curve, actually, with more to say there. Okay, so why else? I actually was sort of interested and delighted to see that I was handed a sort of information packet on the Adlinger Center. And one of the pieces was a prospectus sort of on electrical energy storage. And one of the points that was noted was intermittency. And so the first example on the left of this slide shows variability to cloud coverage in a PV generation curve for a single day. So we see the bump that would model the basic average, and then the intermittency from cloud coverage going over the PV system. And so you could imagine that if I have a storage system operational, I can smooth out those high frequency bumps while also taking care of, for example, the duck curve larger picture function. Then move over to the right-hand side of my graph, and now it's the wind output for just a single turbine. And what one sees over multiple days is that the turbine output, we all know, is weather-driven with respect to fronts and so on, and many ramping events. And these are forecast, of course, but there's uncertainty in forecast. And again, having some backup to make up for forecasting errors is important. Okay, so a few additional points to note on what does energy storage offer. So the places, I think, let's say one is starting out as an entrepreneur in energy storage, a beginning point would be buy low, sell high. You're going to be doing arbitrage, maybe. And you start looking at wholesale numbers, and then you realize that wholesale electricity prices are not that high, and it's going to be a tough sled if one goes there. But the utility or the electrical systems in general have many different pieces that allow them to work. And ancillary services comprise an obvious, or not obvious, but an essential function for the utility system. And so basically, besides supplying energy, the system has to be reliable and has to be able to be made to work even before renewables were brought onto the grid, so contingencies and so on. So the first point here is flexible capacity. And so flexible capacity might traditionally be served by gas generation. And one could note that if one has electrical energy storage with a battery, and I won't say, or with a flywheel also, but it is certainly true, that one has the capability of regulation up and regulation down in terms of capacity. And so in terms of nameplate, the available function is actually twice the nameplate with an energy storage resource relative to a gas generation facility. In addition, a gas generation facility cannot be regulated over 100% of its capacity range. And so it's perhaps more than 2x the availability in terms of what would otherwise be available. Okay, frequency regulation, that is a term that refers to keeping the grid regulated. And this is based on the need for instantaneous balance of generation and load. And so with small fluctuations or substantial fluctuations, because customer behaviors are not predictable, one is able to regulate out these variations and then, let's say, adjust for energy balance in the longer term. Frequency response is a term that addresses transients that occur during a load or a generation or transmission anomaly, and the need to have inertia on the system is inertia is a feature that allows for smoothing and reduction of maximum frequency excursion in such a case of contingency. And with grids that become low inertia, so as one introduces more and more variable generation, renewable generation, for example, traditional generation is reduced, and that inertia, which is provided by conventional generation, is reduced, and then the possibility of electrically making up that function is there, and there are control methods that are straightforward to implement with an electrical inverter and backed up by some energy storage. So it finally takes some, at least seconds of energy storage in order to implement that function. So I spoke about energy arbitrage. Of course, renewable integration. So if one is to execute the fully dispatchable power with a renewable resource, one way is to co-locate energy storage with that resource, and there we go. And ramping or smoothing the output of wind is, in case of inaccuracy in forecasting, is also possible. So another important topic is as the grid ages and one notes that it's time to upgrade resources, a possibility is that maybe we don't have to upgrade resources. So we have, let's say, an isolated part of a feeder, and the feeder is weak, and in order to meet the peak load, one could install energy storage instead of increasing the capacity of that feeder. So it's an example of an upgrade deferral. And then another super popular important topic is microgrid. And so many of us are familiar with microgrid, and in some sense, what makes a microgrid relevant is the feature of having energy storage for providing grid services and resiliency. And so, okay, so what's ideal? And I believe that the features that make an energy storage technology ideal are safety has to go first. So we hear about the challenges with energy storage, and it's fully understandable. We store a lot of energy, stuff can happen, certainly. Cost, it has to be able to fit into the energy framework that our society is accustomed to in order to enable our continued well-being. Multi-hour, in order to go beyond the sort of transient functions that some energy storage technologies are well attuned to. Many thousands of deep cycles. So if we think about that duck curve where I spoke about 2 cycles per day, if we start looking out over years, 3,000 something cycles would get you through 10 years at 1 cycle a day. So I usually think of numbers like 10,000. Maybe that gets you 30 years, maybe that gets you 15 years at 2 cycles a day, but something that is utility able in the sense that utility equipment is expected to last for many decades. And so this is an essential function. High efficiency, I guess it goes without saying. We want to function in an energy environment where we don't introduce new losses. And for many energy storage technologies, self-discharge is an issue, and so low self-discharge is important. O&M costs are perhaps should be factored into cost. And then an important feature of an engineering energy storage technology is its scalability. So one of the technologies that I'll show on the next slide is pump storage, and we can explain that you get to build that only where it's absolutely feasible, and otherwise things are challenging. So controllability, and of course, manufacturability. So that means ready for the real world. Okay, so example technologies are pump storage. So this is basically gravity storage with water. So it basically entails 2 lakes associated with a dam or 2 dams, and the ability then to pump water back uphill as well as to generate with water coming downhill. The most popular energy storage technology after pump storage, so if we look at total installation, pump storage is still the dominant animal. And lithium-ion batteries, though, are clearly the next up technology with respect to their market penetration, first with portables and then with electric vehicle technology. Flow batteries are another type of battery that is often noted in this space, have some challenges with respect to efficiency and some O&M challenges. Metal air batteries are coming along. There are companies that have offer secondary zinc air batteries, for example. So the very small examples are the hearing aid batteries of a primary battery, and there are people playing in that space with secondary batteries. Thermal storage has a few different flavors. In general, it's usually not thought of as an electrical in, electrical out technology, and so it might not necessarily be classified in the space of sort of equivalent to a battery, but nevertheless is important. So used in solar thermal and also in secondary spaces in ice, for example, so pre-cooling. So I understand that the campus here has a substantial function with district cooling. Compressed gas is an example, and there have been companies that have gone at this directly, and it's been a relatively steep climb for them. Supercap is an example, and then Flywheel is the topic that I would like to talk a lot more about right now. Okay, so recent history of flywheels. So let me give some perspective on the meaning of recent. So maybe from the 1980s, and I could explain a little bit about why that's recent. So in some sense, flywheel is as old as the wheel. As soon as there was a wheel and it rotated, it stored momentum and it stored energy as well. In terms of modern times, let's say 1980s, I'd say it's with the advent of power electronics and variable speed drives. So go back before that period, energy in, energy out was accessed mechanically. And so it's relatively challenging to have a system that is highly efficient in terms of rotating losses and so on. But with a so-called modern example, one has a sealed box with some relative vacuum inside the sealed box, and then the energy is imparted and taken out with an electrical machine that operates in that low pressure environment. And driven by the technology that enables variable speed drives, so that's power electronics. And so in some sense, this is the enabler for the modern era of flywheel energy storage. So colleagues beginning in the 1980s sort of outlined how a flywheel could be dimensioned and how it ought to be understood and what it might be used for in a vehicle technology. So some of the people who began this were thinking about pure EVs. And so you do a very rudimentary physics calculation on how much would this thing weigh? And the people who did the very first calculations understood that it looks like it might fly, and it might not fly, but it might work. And the technology might be based on some of the lowest weight rotors per unit of energy storage, and these were the composites. And Some companies went after this, and this is a photo of one of the groups. I believe these are the Rosen brothers working at a company, Rosen Motors. And as we know, the hybrid EVs today don't have flywheels in them. And that meant that all the companies that were looking at that, the few of them, transitioned their business model to something else. They either stopped or they went after something else. Some of them went after the uninterruptible power supply business with backup power. And some companies were able to build many units, notably a company, Penadyne, and another company, Active Power. Not a fantastic business, but nevertheless very interesting, and with special niche markets that are still served by these technologies. One of the companies that also played in the early times transitioned to a function for the grid, namely frequency regulation. This is Beacon Power, and Beacon Power has two substantial plants, one in the New York and one in the New England ISO domain. And then we come to the present era, well, I'd like to say present era, where Amber Kinetics is bringing along a device that supports hours of energy storage as opposed to minutes or seconds. So let me give a little bit of detail about what's inside the box. And so maybe I quickly show you the box again to see what's inside. And so this is a rendering, but in fact, if I were to take one of the company's units and take a saw and cut open the shell, it looks exactly like that. And what you're looking at is a steel rotor, and then on top of that is a magnet that supports the steel rotor. So that's the very basic stuff there. And in some sense, where the tire meets the road is that steel rotor. And, sorry, wrong slide. And I'll give a homework assignment related to one equation in today's lecture. And the equation says that the change in energy, this is kinetic energy, is the change in stress state times a shape factor and times the volume of the rotor. And the shape factor for lots of shapes can sort of approach 1. You never get to 1. And if you try to get to 1, you're going to have a really cool shape, and it won't look like the picture that I just showed you. So shapes are some kind of high number that maybe approach unity. And there's a little bit more in there in that the change in stress state is actually for the detailed people. It's actually the sum of the principal stresses integrated over the volume. And so there are details with respect to whether we're talking about uniaxial stress as in a fiber type hoop or in biaxial stress as in a solid type device. But that's sort of very detailed stuff. And what this really says is that a lot of people, when they first discuss flywheel or they first hear about it, they think it should be heavy, it should be light, it should spin fast, it should spin something else. But really what's important is that the material is strong because you would like to support a lot of stress in the rotor. And it takes a little bit of thinking to get through that. But once you get to that, then you quickly go and say, look at that complicated chart I have, and the thing that I probably ought to optimize is the strength to cost if it's otherwise all feasible. And so what I show is that the next to last column on the right is the strength to cost column, and steel seems to be the dominant animal there in terms of the other materials. So when I mentioned vehicular applications, some of the first people who looked at the possibilities said, oh, I'm going to use carbon fiber. It has a very good strength to weight, and I'm going to then make the battery, so to speak, light so that this works in a vehicle. And it turns out that then if you go over to a stationary application, you don't care about weight too much. You have to have some transport, but otherwise you really want to optimize strength to cost. And so I think it's not so surprising that steel dominates, and our world is made of steel, and that is replicated in this analysis here. So in some of my meetings today, I also learned that steel is a really complicated topic, and in fact, yeah, I've been learning that for a number of years. And so a beginning point is what's the yield, or, what's the ultimate tensile strength, but that's really not defining how you get to use the material. And so it's really a fracture mechanics analysis that defines how many cycles can you get out of the material, and then also the internal state of the material in terms of what's the microstructure, cleanliness, and that impacts on defect and inclusion dimension. And so then there are standard methods for understanding risk of failure, expected cycle life, and they're quite definitive. And these are the things that are used in other mission critical spaces, so in aircraft, aerospace, et cetera. So we're
the rotor is the thing that's likely to destroy itself first? I thought the problem was a bearing problem.
Okay. So how about I talk through this slide, and then we'll talk a little bit about bearings.
Okay.
All right? So it only works when everything works, okay? Just like everything in engineering or even in life. And so we have to have the rotor be functional and efficacious with respect to all its function, and then also everything else. Okay, so yes, it is possible that the rotor could destroy itself, and as anything could. So let's go over to other stuff. And so here's a cutaway. So I mentioned that there is a possibility that if you use a steel rotor, it's relatively easy then to at least conceptually say, I'm going to have a magnetic bearing system. And you could say, that's fun, a fantastic engineering thing to work on, magnetic bearing system. People have them, they work. You're not fully excused from having a touchdown system. So when you turn it off, the rotor needs to land somewhere. If one has a contingency, you still need to deal with it. So you probably don't get excused from having some rotating mechanical bearing system in any case. And so it seems that you have a bearing system, and then that function of allowing the rotor to touch down, especially in an emergency situation, is definitely challenging. And you can imagine that even though all of us very competent engineers can design stuff that might enable that, in order to bring that to product scale, one has to do a lot of testing. So in terms of bearings, there are mechanical ball bearings, relatively conventional, but still special, that are inside the box here that hold the rotor at all times. And then the bearing life is a function of how much load is on the bearing and how fast is it spinning. And by having a magnet that takes up basically 100% of the weight of the rotor, the stress on the bearings is very low. And so, yeah, the bearings can still fail. And the Amber Kinetics company basically tests all these failure modes. And so we've gotten heaps of junk from having stuff fail. And it's actually really interesting, and people learn a lot from carrying out these tests. They're actually, maybe after doing many of them, it's not that much fun, but initially it's really fun to blow stuff up and to make stuff crash. And there's a lot of understanding that comes there. Okay, there's a motor generator inside. So as I mentioned, power electronics are a key technology, and these drive that motor generator, enabling over a wide speed range, putting energy in and out of the rotor. And motor generator is also a very special topic for a flywheel system. So I mentioned that one of the first things is that it operates in a low pressure environment. And as such, it's not that easy to pull heat out of the rotor. It's not necessarily impossible. You have a pretty big rotor, you have a possibility of some radiation cooling, but the bearings actually like to be as cool as possible. And the motor generator then ought not to heat up the rotor to the best extent possible. And so that's one type of constraint. And then another type of constraint is that one would like the motor generator to be able to sort of go quiet. So you could, when I say go quiet, I don't mean quiet acoustically, I mean quiet with respect to drag. So the permanent magnet motors are really popular. They're probably dominating in the EV space, and then a whole bunch of appliances and so on. And there's a reasonable reason for that, is that if you look at the sort of torque per volume or torque per weight, they probably maximize that. And then in some examples, that carries over to cost optimization as well. Magnets are not free though. But when you have magnets, the magnets spin and they always cause some residual loss in whatever the magnetic field impinges on. And so there is a substantial challenge there. And the motor generator inside this machine actually doesn't have any magnets. And so it can be basically made to be quiet. So you depower the motor generator, just metal spinning in the vacuum. And now we talked about the rotor having adequate strength to store the energy. And the motor generator has a rotating component that is mounted on that rotor that co-rotates with it. And so rotors that have lots of features on them are also challenging for their rotational mechanical design. And so the motor generator is a special thing. Okay, power electronics. There are special examples where things can be challenging with these applications. The synchronous frequencies for some of these examples are relatively high. So in some sense, 60 hertz is our popular number in North America. Lots of electric drives are sort of centered around 60 hertz as a sort of reasonable baseline speed. However, some of these applications have electrical frequencies that are up in the hundreds of hertz or even into the kilohertz. And so these features may define needs for switching frequencies in power electronics that are substantially higher than what is convenient. And so in some cases, that may be a challenge. Okay, then controls and communication. And then finally, how do you build this thing? So EPC, that means construction, logistics, and so on. Okay, feel free to interrupt me and say that I skipped over an important detail that you were curious about. I'm willing to discuss more if you prompt me. Okay, so this is a short data sheet for the Amber Kinetics flywheel. So basically, power and energy are ratioed at 4 hours. This is really a design choice. It's not fundamental. So with electrochemical batteries, there is a physics that often relates the ratio between power and energy. In these examples of a flywheel, the physics is really fully decoupled. So one has energy in the rotational inertia of the rotor, and then power in the motor generator and the power electronics. And in principle, there's a lot of degrees of freedom in design, and the 4-hour ratio is largely a stab at where the market is, partly driven by the California market. Okay, cooling, it's good not to require active cooling, and we know that some of the electrochemical battery systems, especially lithium-ion, really like to operate at room temperature. And so an HVAC system is often necessary in order to guarantee life for a lithium-ion battery. Okay, in terms of efficiency, it turns out efficiency is quite good, greater than 86% round trip for this thing. There's no limitation on cycling. Of course, it takes 4 hours to discharge fully, if that's the objective, 4 hours and some change to charge, because one has to put back the losses. And then other regular details, it's pretty fast in terms of response, 1 second time scale. And people always ask, what about the bearings? What about the drag loss? It's actually really low. And that's because bearings work well, magnet works well, vacuum works adequately well, and the drag loss is quite low. Some people also ask, does that magnet take a lot of power to keep the thing lifted up? The answer is not very much. It's actually an electromagnet, but it doesn't take very much power.
May I ask a question?
Sure.
About the efficiency, I suppose the way it's defined here, you know, you charge and then you immediately discharge it with no sort of idling in between time. If you apply it on the duck curve, I think you called it in California, you know, over a 24-hour operating period, what kind of efficiency do you end up with? It must be a little bit less than that, I suppose.
Yeah. So nevertheless, if you look at that, I mean, you have to now remember, I don't want to go back to the duck curve, but it's perfectly reasonable that one might charge during the midday and then discharge during the evening peak. And so the amount of dwell time may not be that long, as 24 hours. But nevertheless, one would integrate up, and yes, you'll have some more losses, and then 86% would be degraded potentially. Now, this is a commercial number, 86%, and the engineers at Amber Kinetics basically forced me to say that, but lots of the examples, typical is actually a substantially higher number. And so this is some fairly honest reporting in terms of numbers there.
Excuse me.
Yes, sir.
Could you elaborate slightly on the design life and that failure mode and O&M impact and overhaul? What is that? What do you mean when you say 30 years on design?
Right on. Yeah, so how long does the basic hardware last? So there are O&M intervals. So there's, with very high probability, the bearings last for 7 years, and they're replaceable in the field. And so that's one example of an O&M step. There are additional vacuum components that have some O&M requirements, and I'm not usually doing sales for the company, and so I'm actually not fully informed on the very details of the schedules there.
So I also have a question about efficiency. I'm curious, does the efficiency depend at all on the amount of energy you have stored at any given time? So in other words, the speed of your rotor will be efficiency.
Yeah. So for like what you might call partial cycles, would it be different? Yeah, it's definitely somewhat different, and it's not radically different, but there's a physical basis for why things are a little bit different over different speeds. So I have a little bit of data that I'll get to in a moment. And so when I put that up, I'll try to remember to say a few more words about that. Yes, sir?
I read somewhere that these flywheels have a little bit of an issue where as the Earth rotates around, they conserve angular momentum. So they experience something akin to a Foucault pendulum.
Yes.
How do you deal with that?
Yeah. The poor bearings have to keep pushing the rotor back into keep it vertical relative to gravity in the rotating frame of the Earth.
Does that consume energy?
Not energy, because there's no work done in doing that. Or from a I don't know what the number is for the freshman mechanics physics class anymore, but there'd be no work done. But it puts a tiny load on the bearings, and so that's one of the calculations that would be called Coriolis force. I think would be the term. You can get the number, and it's basically the torque required to rotate the angular momentum with the Earth's rotation. But yeah, it's a good point. And there's all kinds of like little follow-on trick questions about if it was on the North Pole, what would happen, and which way would you rather rotate, and so on. So, yeah. Was there another question? Okay. Okay, yeah, here's where there's some data. So on the upper left is a charge, discharge, and dwell curve. And so it's showing the flywheel being charged up. And we all know that one of the formulas for energy storage in a kinetic thing is it goes with the speed squared. And so there's a sort of parabolic red curve, that's the speed curve. And the speed is on the right-hand axis, or state of charge is on the left-hand axis. So it goes up to full charge, then it dwells constant speed, and then it is discharged after a few hours. And then up on the upper right is the average discharge power as a function of state of charge. And again, it's sort of in utility type units. I think it's kilowatt hour loss per hour. It's like, really? That's also called kilowatts. So in fact, at full state of charge, the loss is about 90 watts, and at minimum state of charge, it's about 30 watts. So that's one thing that would change the efficiency as one takes minor cycles up and down. The other thing that would change the efficiency is that the sort of optimal operation of the motor generator is slightly different, but it's not radically different. It would be like fraction of a percent different and based on operating point. Then on the lower part is basically a transient response, and this is what is sort of relevant for doing the frequency regulation function where high-speed responses are necessary. And so things are really limited by communication, and I'll show another overview diagram in a moment, but we see that it's actually a third-party inverter that connects to the utility. And so we can't be any better than a third-party inverter can. Okay, so here's a picture of how things are connected together. And believe it or not, the thing that is shown installed below grade on the left is actually not one flywheel. It's meant to be an array of flywheels. And my diagram ought to have an array. And power is aggregated on the DC terminals. So on top of the flywheel is the so-called power electronics box. It's basically an inverter. The motor wants an AC voltage waveform. AC currents flow at the same frequency there. And frequency varies over the speed range for the flywheel. So if we have multiple flywheels, each one can have its own speed. They're normally very similar in speed, nearly identical, but they don't have to be identical at any moment. We have controls that keep them regulated if that's the wish of the system. The DC power is aggregated to a grid tie inverter and then point of interconnect to the utility. Then control and data is sent to our flywheel management system. So that's also an Amber Kinetics system product, and then up to the cloud for data storage, as well as command and control. Okay, so here's more nuts and bolts on how stuff is installed. So this is, I believe, at our test site in Central California. This is King City, California. And these are basically corrugated metal pipes. So this is just like the water conduits that go under roadways and so on. So designed for below-grade installation. And there's a seal on the bottom, and the flywheel unit is basically installed at the bottom of that can, and then a cover is installed on top of the can. So here's the next picture. A flywheel being lowered into the can. 2 of the covers are already installed in this 4-unit array. Okay, so.
How big and heavy is this thing?
Yeah, yeah, good point. So the diameter of the housing is about I think it's about 4.5 feet, and or 1.2 meters or something like that. The whole package is about 10,000 pounds. The rotor is about 5,000 pounds, so about half of it. And so kind of dense. Okay, these are some of the company's projects, and more going on. So this is very early, and you see the device at the top left was one of the first very few that were built a number of years ago. And this is at our test site in Alameda, California. So this is a former naval base that is in the East Bay community, so that's close to where our company headquarters is. And you see that it's nothing like what the thing, or it's not exactly nothing like, it's still a can, but it's somewhat different, and it's in a more conventional, like, transformer vault, the installation. But otherwise, things are pretty much similar to how things have gone. One of the early units was installed at a Subic Bay site in 2016, and this is still not the corrugated metal can installation, but nevertheless is here, and that's sort of the christening of that device. We have more utilization. We actually make a lot of use of our King City test site, and we've had a fairly long cooperation with the Enel utilities. That's an Italian utility that has a pretty large footprint globally. And we've done a series of demos with Enel, and this is part of our team and some of the Enel engineers in the picture. This is a fun project that ran for over a year at Hawaiian Electric. And let me remember what my graphs are. So the top blue is solar generation. This is a single unit device. And the flywheel is commanded basically to absorb energy nominally during the day. So we see that the flywheel output is in green. It's below 0. So it's basically serving that duck curve type function. And then the system is saying, you're going to discharge in the evening when all the Hawaiians go home, and maybe they don't use air conditioning so much, but they definitely cook. So they have a lot of electric utilities, in some cases, surprisingly. And then the red curve is the net. And so we see that the energy storage flywheel is able to average out or mitigate the peaks, and then to mitigate the overall bump in the sort of duck curve type of feature. Okay, we have an installation in Lhasa in Tibet. And so it's sort of cool because it's cool there, and it's also at high altitude, and so questions about what happens if the altitude is high, not too much, and things work pretty well. We have a newly online installation in Massachusetts, West Boylston Municipal Light, 16-unit array, and shown here. And we have a demo site in the Philippines on one of the Philippine university campuses. And so the Amber Kinetics company has headquarters in Union City, California. That's East Bay, near where I live. And then also in the Manila area. So corporate headquarters in sort of downtown Manila, and then functional places for manufacturing, and then for demo and testing at this university campus. So I visited there before this was built. It was sort of like, not exactly jungle, but something like jungle. Came back a little bit later, and this is what stuff looked like. Actually, someone else took the picture. But we have not fully built out, but a plan for 125 units. That's close to a megawatt system that's going on at that campus. Okay, so that's the slides that I have. We've operated for many units for many hours, and of course that number keeps going up, and so this is a snapshot from a few months ago. So thanks for your attention and questions during, but maybe there are more questions, things that I've managed to skirt by that you'd like to explore. Happy to do so. Yes, sir.
Flywheel needs to be buried underground.
Yeah, so one of the usual, or not usual, but one of the challenging questions. So I mentioned that the rotor is built with basically the same kinds of care that go into mission critical technologies. And so the worst case kind of failure is that the rotor comes apart. And that's why it's below grade. So we've done careful studies of this experimentally, as well as, let's say, physics type studies of like, what happens when a projectile goes into soil? And it's also a fun topic to study and then to do the experiments. And so that has been carried out. And so we operate below grade for, let's say, the foreseeable future because we cannot risk having a worst case event occur. It's never happened that we've had an unplanned failure that would be hazardous, but nevertheless, we need to be careful as a young company. So after some years, there's lots of other utility equipment that poses all kinds of dangers if one were to finally say, this is possible. But lots of things are possible and there are risks, and a more careful risk analysis is let's say, just beginning. So the risk people need to get numbers and get on it.
All right, so it's to limit damage from rapid unplanned disassembly.
Thank you. Like that.
Just a question about the vacuum. Does it require any additional pumping, or how is it sealed up, and what's the maintenance level on that?
Right on. Yeah, so at present there's a mechanical vacuum pump, and it runs on an intermittent schedule. And So let's see. So in terms of sealing, there are some relatively conventional O-rings that might be in any type of sealed system. Otherwise, it takes a lot of attention to cleanliness and process in order to have a vacuum system operate. And additional steps are, for example, pre-baking some of the components to drive off moisture, as an example.
What's the cost per kilowatt hour?
Yeah. Yeah, it's a tough question because I probably shouldn't be the one to answer that, especially on record, as I understand here. The cost per kilowatt hour, and the other way that question is sometimes posed is it an install all-in cost to AC, for example. And the number is in some number of hundreds of dollars per kilowatt hour. And the reason that I wouldn't want to go on record straight away is that it's normally not my job to do the sales part of the company function.
I'm just wondering, that's one of the drawbacks, I would think, and also the weight. A Tesla Powerwall is about 14 kilowatt hours, and I think it's about 300 pounds.
That's a fair statement. So there are a bunch of spaces where the Powerwall clearly is transportable. Maybe somebody would like to think carefully about installing that in a garage, for example, because we know there's a hazard there. Nevertheless, fair point on the weight. They're not free also, the Powerwall. And the system costs are also a function of where they're implemented. So utility scale and behind the meter are basically have different cost frameworks. And so even having a single number is a little bit too simple for that type of question.
Hey, so maybe a cost-related question you can answer without making your friends in the sales team mad. Looking forward, what are the major components of cost in the system, and how do you anticipate those will change over time as the technology scales up, as manufacturing scales, through continued innovations? What's the potential there?
Yeah, thanks. So I think it's technological improvement. So if one is able to improve the energy density, then the balance of system costs basically fade away. And that can happen in two ways. One is one improves the energy density of the technology, and then one increases the size, scales the unit. Basically, you look at a unit, it's got a box around it. The box is a little bit bigger, that's not such a big deal. It's got feed-throughs, it's got feet, it's got paint on it. All these things are basically one-offs that need to be addressed. And so scaling is really important. And so this is sort of the entry-level product for the company. And so I believe that there is a very competitive curve for the future of this. So I think in some of the discussions today, we were talking about the experience curve, and that we've seen a brilliant curve for silicon PV. We've seen a good part of that curve for lithium-ion batteries. And if you take a new technology here, that's also a reason that it's sort of a pretty tough question to say, you made 50 or 100 pieces so far, what's your unit cost? And so with that scale, it comes a very good opportunity for reduction.
But the economies are at a unit scale, not manufacturing experience. It's more like wind turbines than solar or lithium-ion, which are tiny modular units that are arrayed in mass.
So let me understand.
So your main cost reduction comes out of getting a larger scale.
Oh yeah.
That's similar to the story for wind, where now we have 12 megawatt offshore wind turbines that are much cheaper,
right, without
being that much larger.
So you're saying
you're not going to go up to 12 megawatt size, so I'm curious.
I'd love to, but not likely. So I can imagine units that are, for example, 10 times larger in terms of capacity.
So one of the challenges with batteries as energy storage is that power and energy are linked in a way, right? And you you can't necessarily get the maximum in both all the time. I'm curious if you can comment on that in the context of the flywheels, and then also comment on what really sets the maximum energy density or maximum power that you can get out of these systems. And this was a non-cost related question.
Yes, thanks. Yeah. I thought I did a pretty good job on the maximum energy. So, maybe this is a little bit superficial, but it begins to explain. So maybe replace strength as a sort of just placeholder number with something like a life cycle rated strength. So if one sets out for 20,000 cycles, what is the usable stress and component? And so that would define that basic function for the rotor. And in terms of how much power, there's probably a real limit where things get to be on the hairy edge, but we're so far from that. Like if one were to say, make that thing charge and discharge in 1 minute, I think that's also in the range of basic regular technology. And if one wanted to cycle at that up and down 1 minute many times, thermal management would become more of a problem. But in terms of what can be done, yeah, no problem. Say, Seth, go design the motor for that. Say, yeah, I'd love to. Yeah, that's fine.
We have 2 more questions. First over here.
I was wondering what was your engineering constraints for coming to, I think it was 8 kilowatts was per wheel.
Yes.
So how did you come up with 8 kilowatts being the base unit? So, because now you have to array all these to get to the higher power levels. What is preventing you to going to even larger systems?
Right. Really nothing. Okay. I think with a startup, at some point there's like 5 guys in the room, and one understands like what size equipment can you build an initial facility for. And so some things happen sort of, unfortunately, happenstance. And then when the company now has 100 people want to be a lot more analytical about what would happen next. And so it's very much the size and weight of material that was sort of manageable with equipment that was understandable to our initial team that defined the size of the rotor. And then the 8 kilowatts is largely the 4-hour ratio, and that's largely defined by the California capacity market as the initial target application. So target applications are substantially different for the early sales that the company is making. And so by all means, that's a perfect question, and we have people in the company that have titles like product manager that have that job of addressing that. In the earlier stages, the founders basically put their finger up and look around and say, aha, we go here. So.
Thank you.
Last question. Is the scaling direction diameter or along the shaft or both?
In terms of making it bigger? Yeah. So certainly both are possible. It's a really good debate topic, including fairly hotly debated among my colleagues. I love wide and flat for lots of reasons. You can look at gyroscopic stability. That's really nice. Rotation speed is lower as you make it wider for the same mass. That's kind of good for bearings and so on. If you look at footprint, it's kind of good to go a little bit more vertical. So it's sort of all over the place in terms of what's good.
Okay, with this, let's wrap up the session. And usually it's I showing the visitors around the campus, but in this case, it's Seth showing us around the campus. All right, thanks. If you have any questions, you can come up and then talk to Seth.